Welcome to my Lab4 report oscillation. The purpose of the lab is to analyze the oscillation motion of the spring mass system in tracker and compare the observed motion with the predicted motion in glow script. The fundamental principles used here are the following two. First is the Newton's second law. It is used to update the position of the mass. Actually, in the end, it's used to update the position of the spring. The energy principle is also used here to calculate the energy change, which is that delta E is equal to delta EK plus delta UG plus delta US. Delta EK is the change of the kinetic energy, delta UG is the change of the gravitational potential energy, and the delta US is the change of the spring potential energy. Here is the tracker model that I constructed. The starter frame is 20 and the end frame is 130. The calibration stick is 0.7 meters, which is the vertical distance between the fixed point and the center of the mass. The mass is equal to 0.402 kilograms. The coordinate system I constructed, I used the fixed point as the origin. Here's the data that I extracted from the tracker model. As you can see, the first is the initial position. The x component is minus 0.096 meter, and the y component is minus 0.645 meter. The time interval here is 7.882 seconds. In order to calculate the spring constant, we use this formula here. The Ks equal to 4 times pi square times m divided by period square, which is 5.857 Newton per meter. In my model that I calculate the t, use the x component, and is the average period of the 3-time period. And then in order to calculate the L0, I choose a state that the string is at rest vertically, so that the mg is equal to the spring force. So that L0 is equal to L minus mg divided by Ks, which is equal to 0.0274 meter. Here's the computer model that I constructed. For these lines of the code, I constructed the necessary values for the spring and energies. Here's the calculation part of the computer model. First, I calculate the initial energy, and then is the gravitational and spring force. And then I use these F net to calculate the position of the ball. And then use the update of the position of the ball. I update the spring. And then calculate the energy change of the spring and of the kinetic energy, of the gravitational potential energy, and the total energy. As I run this code, this is the result that generated. The red line here is a computer model, the blue line here is a tracker model. As you can see, the similarities is that the shape of the both models are roughly consistent. They are both in oscillation forms with roughly the same amplitude and period. But there are some distance existed. First is that you can see as times went by, the tracker model lag behind the computer model. I think there's some reason because the computer model is the ideal model, which is a closed system. So when there's no external force, it will oscillating constantly. But the tracker model is in the raw setting, so that the spring will slows down and at the end it will stop. And you can also see that the second difference is that the observed model is not perfectly smooth curve. There is some angles here, here, and here. The possible error here is that the center of the mass is not marked perfectly. Here's the first what does it mean question. For your model system, is the energy principle satisfied? The answer is yes. The system that I choose here is the mass plus the spring plus the earth. According to the energy principle, we know that delta E is equal to the delta EK plus delta UG plus delta US. The system is an isolated system, so there's no work done by the surroundings, so the delta E is equal to 0. As you can see, the origin line is equal to 0. And you can also see that the change of the kinetic energy and the change of the gravitational potential energy and the spring potential energy are all equal to 0. Here's the second what does it mean question. It's to make the two separate estimate of the oscillation period. As I construct my model, I estimate the oscillation period by the x component, which I calculated here is t equals to 1.646 second. But as I can also calculate in the y component, which is t equal to 1.519 second. They are very close to each other, which is mean as the mass oscillating that in the y and x component, the period of its oscillations are very close to each other. So maybe in order to have the much more accurate calculation of the period, I should plus the 2 and find the average time period. Here's the conclusion. The general shape of the observed model fit the predicted model, but the observed model lags as time goes by, probably because the raw model is not a closed system and dissipated force exists. Thank you for your watching.